So, welcome to the next in our series of science and cooking lectures. So today, as always, I'd like to acknowledge our sponsors for the class. We have the usual sponsors, Jose Andres, the Think Food Group, Alicia, who sponsor us both with financial support and intellectual support, Montferrand, Whole Foods, who provide all the supplies, Whole Foods on River Street, provide all the supplies to our lab, because after all, we eat our lab in the class. Fusion Chef by Julabo, that provides the immersion cookers. Catalana Casa de Bank in Catalana. And we have two new sponsors, Food and Wine and Lexus, who have taken up the sponsorship of these public lectures as well, and we thank them all. This week in class, we were very, very lucky and fortunate to have a group of wonderful chefs from the area who participated in panel discussions and told us about what they do, raised many questions, showed how many things that I said about the science were not quite right. They didn't agree with all the things they did. But we were very fortunate to have all of them, and we thank them all for participating in our class. And then next week, after Thanksgiving, the Monday after Thanksgiving, we have Bill Yossis. He's the White House pastry chef. He'll be talking on Monday. And then on December 4th, we have a special lecture by Ferran Adria. For that, you have to get tickets. They're free, but you have to get tickets at the Holyoke Center. They'll be available starting the 29th of November. There will be also overflow rooms where we'll broadcast if you come and you can't get in and you want to be here when he's talking. And then tonight, we'll have Nathan Myhrvold, but of course, before we do that, we have to have a little bit of an opportunity to have our equation of the week, as we do each time. So I'll spend a couple of minutes telling you about that. One thing that let me announce now, that Nathan will sign books at the back outside at the end of the lecture. And there'll be also his modernist cuisine will be available for purchase outside after the lecture. So in the meantime, this is a traditional season, and so this is an example. Let me move the cursor out of the way. This is an example of what many of us will be doing later this week. And we wondered in class, how could we understand something about how long it takes to cook the turkey? Well, we can look it up, of course. There's tables of cooking times. But how can we understand these tables? Where do they come from? And we learned earlier in class, and we've discussed it in these public lectures, that heat, when it propagates through, or temperature when it changes, and therefore heat when it propagates through a material, propagates via diffusion. And this is the equation that tells you how long, the time it takes for heat to diffuse a certain length, L, some distance L, given the diffusion time, or the diffusion coefficient for heat, which is units in this case of meters squared per second. So this is something we learned before. It tells us something about how long it takes, but we now have to somehow relate that. If we want to calculate cooking time, we have to relate that to how fast or how long it takes to change the temperature. So we need to know something about what the temperature is given this type of propagation of heat. And temperature really does make a difference. Here, for example, are some pictures of steak, and these are cooked different ways. These are cooked with the traditional way with a grill, so it's charred on the outside. It's got these different textures as you go through it. This is cooked by the sous vide method. So in this case, we use temperature. We use a much higher temperature, and we wait while the heat diffuses in. We would like to know how long it takes to change the temperature by a certain amount. In this case, we cook with a method that raises the temperature of the whole food, all of the food, to the same temperature of the bath in which it is immersed. So there, in either case, of course, the temperature determines or helps determine something about the texture, the flavor of the food. Similarly, we've talked about cooking cakes. This is a chocolate cake that cooks from the outside, and as it cooks inward, it gets harder, it solidifies, depending on how long you cook it for. So the temperature is diffusing from the outside, from the hot oven, going in. And here are some, in fact, some data, some measurements of the temperature made while the cake, while this molten chocolate cake was cooking. Here the temperature is measured in the middle. Here the temperature is measured on the outside, and you can see there's an increase in temperature until it reaches some final temperature. In this case, notice what the final temperature is. It's right around boiling point, so it's being heated up, and it's not quite boiling in this case. So how can we understand that? Well, I don't want to go through all the details, but qualitatively we can understand it, that the temperature, the heat is diffusing in from the outside, and how fast it takes, the time it takes for it to diffuse, for the temperature to change, depends on the temperature difference. So if it's very, very hot on the outside, there's much more heat diffusing in. It diffuses more rapidly. But as the temperature approaches that of the outside, the rate that it diffuses in slows down. And so, in fact, this leads to an exponential dependence on cooking time. And we can use this as an approximation and learn something about the position dependence by using that time constant, that time that you calculate using the diffusion coefficient, the diffusion time. We use that as the characteristic time for the exponential, and that will give us the length dependence, and it'll tell us how long it takes to cook a certain, to raise a certain position of the food up to the new temperature. And so how can we calculate that? Well, of course, we need to know something about the size. So here's a turkey. So what do we do when we want to calculate the size of a turkey? Well, I keep telling you I'm just a physicist, so immediately I say it's a sphere. It's a spherical turkey. And so if it's a spherical turkey, I can calculate what the size is by knowing that the density is just the volume times the density. And I know that this gives me the weight. From the weight, I can calculate the mass for the density. I assume, of course, that the density is just that of water, because food is almost all water, so I'll assume the density is 1. And this allows me to estimate, using my spherical turkey approximation, estimate what the size is. This is about 10 centimeters in radius. So from that, I can calculate then what the temperature is, and I won't derive this equation, but here is the equation of the week taken from that exponential form. It looks rather complicated if you're not used to looking at equations like this, but it's really not that complicated. It just depends on the external temperature, the initial temperature, and the temperature at which you're trying to heat things to, plus this diffusion coefficient. And here is where you get the length, knowing what the size is. This is actually not a bad approximation, and you can see that if I use this simple spherical turkey approximation and that equation to calculate what the cooking times are. Here are the cooking times. These are the empirical times in the table, the cooking table, and you can see that I can calculate this really quite accurately. So this very simple approximation, plus this idea that heat is diffusing in from the outside, and the only diffusion coefficient that I really need to know is the diffusion coefficient of heat through water, really allows me to calculate what the cooking time is, and to explain why you see the tables when you see these particular tables, at least for turkey. Of course, it's more complicated. Is it a stuffed turkey? Is it a not stuffed turkey? And all this. But those are complications that we really don't deal with when we approximate the turkey as a sphere. This actually is the real equation of the week. I didn't want to show it to you because this would be frightening even to me. But this is actually an excellent introduction. This has both the spatial dependence and the time dependence. And this is an excellent introduction to our speaker, Nathan Myhrvold, who was actually trained. He has a PhD both in mathematical economics and theoretical physics. And here's a paper that we found that he published when he was still, I believe, a graduate student, since it's from Princeton University. And these are the kind of equations that he knows how to solve. So he clearly can solve much more complicated equations than even I can solve. So Nathan was the CTO at Microsoft for a number of years, and he now has a venture called Intellectual Ventures. But his love is also understanding something about cuisine. So one of his contributions is to develop this table of cooking times for sous vide cooking. And I'm sure when he calculated that, he used the full equation, not these simple approximations that I used. I spared you that, you see? And he's written, of course, this absolutely wonderful book, Modernist Cuisine. He will sign copies, and they'll be sold at the back after the lecture. But in the meantime, he's actually going to tell us something about his journey combining both science and cooking. Nathan.
Okay. So first I'm going to tell you a little bit about my book, and then a little bit about the science in the book. So there's lots of big, thick, wonderful books that explain cooking technique. The Culinary Institute of America has one. Cordon Bleu has one. But those are only for classic techniques. And if you looked in those kind of books, you would find no technique that is younger than about 30 years old, and most of them are older than that. There's a lot of books on the science of cooking. Harold McGee started the whole thing with a book called On Food and Cooking in 1984, hugely influential to me. It's got a more recent edition. These books are great, but they don't show techniques for the chef. They're about the science of cooking for its own sake, which is a wonderful thing, and they've influenced chefs, but they're not cookbooks. There's also a few books on a single technique. The one at the bottom is by Joan Roca, who's spoken here in this area. In this course. These books are great, but they only cover one technique, in that case, sous vide cooking. So I realized all of this. Oh, finally, there's big books by modernist chefs, Heston Blumenthal's Big Fat Duck Cookbook, a whole series of wonderful books by Ferran Adria, who has spoken here and will be in December 4th, Grant Achatz, who's also spoken here. These books are great, but they explore one chef's vision of food. And as big as they are, they don't have the page budget to explain step by step, here's how to do the things. Particularly, they don't tend not to explain the things that these guys think are pretty elementary, which is not necessarily what other people think are elementary. So these books are terrific. I find they're best if you already know how to do it. What I realized when I got interested in doing this is that chefs around the world, including these guys who are the people speaking here in the course, chefs around the world had invented lots of cool techniques. And food scientists had figured out lots of great science. But it was scattered all over the place. In fact, there was lots of things I thought were a fundamental foundation of cuisine for the 21st century, but instead of being treated as fundamental ideas, this guy had 3 tricks, and that person had another 4 tricks. And a food scientist had figured something out, and he published it for other food scientists, but the chefs didn't know. So, God, wouldn't it be great if you could pull it all together in one place? So we did, and that's a modernist cuisine. It's got 1,500 recipes, so it's a cookbook. But it's got a lot more than that. It's got a big section on history and science. We have chapters on the physics of heat, for example. We have lots of things on equipment, technique. We go through ingredients in enormous detail, describing the best scientific knowledge about meat, about plants, about all these other areas. And then finally, because the book is kind of big and kind of pretty, we also have reprinted all of the key tables and recipes on what we call the kitchen manual, which is printed on waterproof washable paper. So here are some fun facts. 6 volumes, 2,438 pages, 1.1 million words. If you put them into a single line in Microsoft Word, it would be 7.5 miles long. I am not sure why you'd want to do that, but I thought it was cool. We took about 150,000 pictures to get the pictures in the book, and hey, 3,200 of them are actually pretty good, so we put them in the book. 1,522 recipes. Recipes inspired by or adapted from 72 of the best chefs around the world, most of whom gave us their consent. A few had passed on. 6 research chefs, 44 writers, editors, and art staff. 42 pounds unpacked, and my favorite statistic, 4 pounds of ink in one copy. It's amazing when the printers make a blank book for you. Of course, there's no ink on it. And I said, well, it'll be this size, right? And they said, well, except for the weight and thickness of the ink. And I laugh. They said, no, actually, the ink's going to add about 3/4 of an inch to the thickness, and it will weigh 4 pounds. And that's because on a full-page photo, there's 1/1000th of an inch of ink. Well, you got 1,000 pages that have that. That's an inch of ink. So when I say 4 pounds of ink, a lot of people say, what's up with the ink thing? You know, I've got a history of being a digital guy. This is the 21st century. Why didn't I make it in digital form? And when we started to really lay the book out, iPad didn't exist. Kindle was the only ebook available at that time. This is 2.5 years ago. And we considered what it looked like in Kindle. Here's one of our test pictures. This is a picture from the book, and it kind of loses something on Kindle. Because we made a fundamental decision early on that we wanted to use dramatic, beautiful photographs to communicate the ideas to people. For some people, the notion of having science in the book would be considered daunting or maybe intimidating. For other people, the idea that we would be covering advanced cooking techniques in the kitchens of people like Farah and Adria, that could be pretty daunting. So let's use dramatic photographs to try to show people things rather than just tell them, and to try to get them sucked in and hooked on the idea of the book, and before they realized it, they might actually learn some science, or they might have actually learned some cooking. Now, when you take those big, beautiful photographs, you open up, the book is huge, and you compare it to what you'd get on an iPad, you'd be like flicking all day long and expanding and contracting. And at some point, I'm sure we'll make an electronic version, but not at the moment. Oddly enough, there's never been a better time to make a paper book. The same digital tools that let you do digital delivery actually let you print really effectively on the other side of the world and lay all this stuff out, so we were able to do it. And do it without we are the publishing company, by the way. It's sort of like when they say if you represent yourself in court, you have a fool for a client. It's like that. So this is just one example of the cutaway photos that we did to try to show people what goes on while you're cooking. This is a picture of a traditional braise. And way back when, braising meant you took a cast iron pot, Dutch oven is one name for that. You'd put coals below it, you'd keep coals on top. It would heat radiantly from the top, like a broiler would, and it would wet heat from below. And essentially no one braises this way anymore unless they're camping. Today we braise typically in ovens. It's actually a somewhat different process. But this picture shows the idea of having a cutaway and of then with those the various text blocks and pointers discussing what's happening while food cooks. Here's our version of the equation of the week. We wrote ours in fire. Okay? So now I'm going to talk about modernist cuisine, the movement, as opposed to modernist cuisine, the book. And there's a bunch of interesting things. I think the first point is that the kitchen, that cooking really can be an art. And there's a big difference in our society between an art and a craft, between an artist and an artisan. And a lot of aspects of cooking are treated like it's a craft. A craft is a perfectly respectable thing, but it's different than art. And most art critics would say the difference is that art is about trying to engage the people's minds and emotions deliberately. That they're trying to engage in intellectual discourse with them. So I think cooking can be an art, but it's also a science. I was being interviewed for the book by a journalist in the UK who was, I didn't quite get the point of the book, I think. And she said, so what made you think that you should put science in the kitchen? I said, actually, science was always there. I'm trying to take ignorance out of the kitchen. Because, of course, science is about the laws of nature. And science governs how you cook, whether you like it or not, whether you know it or not. And I find it's usually better in life to know it rather than not. Now, there's also an interesting philosophical point. Recipes are about saying, do this, do this, do this, and then you get the right result. And classically, recipes didn't actually tell you all that much. Escoffier was one of the great cooks. His book in 1903 helped solidify French cooking's preeminence around the world. And if you read an Escoffier recipe, it will have proportions, it'll say to mix things, and then it has these wonderfully informative sentences like, cook until done. Because in Escoffier's day, cooks were apprentices. They went when they were kids to go work for a master chef, and they worked their way up, and they damn well should know what cook was until done was about. And the point of a recipe was to store up a bunch of facts that were shorthand to someone who'd gone through that apprentice system. Today, not so much. Today we like to understand things. And one of the reasons we like to understand things is we like to create. And this new kind of cuisine is about creating. When you go do something different, it really helps if you understand what's going on, as opposed to simply knowing a rote set of instructions. And so the idea here of modernist cuisine, the movement, is melding the art and science of cooking. Starting in the late 70s, new technologies that had never been involved in cooking started coming into the kitchen. And starting in the mid-80s, a number of chefs, Ferran Adria, one of the earliest and the most prominent, but many chefs, started innovating and doing something really new. And an analogy I like to use for that is the Impressionist artist. This is a painting by Monet. This is, in fact, the painting that gave Impressionism its name. It was ridiculed. When Monet and a variety of other artists started rebelling against the academic art that had come before that, started making paintings like this, that were their impressions of things. They weren't literal photorealistic things. Of course, photography didn't exist. That's one reason they weren't photorealistic. But the other is that they were more about emotion. And they were totally derided. And a French art critic actually wrote this heavily satirical piece calling them the Impressionists because all they caught was a mere impression. Well, these guys said, okay, call us Impressionists. That led to a whole sequence of rethinking art. This is an example of Louis Kahn, the Salk Institute near San Diego, example of modernist architecture, modernist dance, all aspects of human aesthetic life started to be renovated, starting in mid-19th century moving forward. People rethought them, and they said, you know, this idea of constraining ourselves with rules, that gets in our way. We should break rules. We should create a new kind of art. It was not popular. These are two cartoons that we have in the book. They're both from Paris magazines, the 1870s. The first shows a pregnant woman being refused admission to an Impressionist gallery because the paintings are so ugly they would make her miscarry. The second shows the Turkish army brandishing Impressionist canvases to frighten their enemies. It was a weapon of war. The paintings were so ugly you could use them as a weapon of war. Now today, the Impressionist paintings are probably the best loved paintings on earth. Traditionalists love them, modernists love them, everybody loves them. You know, if there's a Cézanne or a Van Gogh show at a museum, the line is around the block. What happened? Well, when you change a convention, people notice, and people react, and they react strongly. And the more passionately they believe about that, the more they react. Religious wars are about that. But in a secular sense, the modernist revolutions in these various disciplines were about that. So what was modernism? Deliberate break with tradition, celebration of aesthetic values beyond realism, embracing new tools and techniques. Well, this started happening in cuisine in the mid-1980s, and my book and this whole movement is about dining as a dialogue between the chef and the patron. Now, that's not what happens in a steakhouse. Steakhouse, you go in and you order the exact piece of meat, you say how many ounces it is, what temperature you want it done to. It comes with nothing else on the plate until you order the side dishes, you order the other stuff. If you are a chef in a steakhouse, about the only thing you get to do is figure out the proportions of the chopped salad. Okay, that's it. Everything else is totally dictated by the diner. This new cuisine is different. It's about breaking the rules and doing things in a different way. Creativity trumps tradition. Surprise is actually part of it. A lot of modern art is about making us realize that we implicitly had all these rules deep in our heads. There's a demo we do, we wonderful do it today, but we don't have time for everything. It involves something we call hyper-decanting. You take a bottle of fine red wine, you put it in a blender, and you hit frappe. And there's two reasons to hyper-decant. One is because all of the benefits you get from decanting, you get more so with hyper-decanting. But the other reason hyper-decants is the looks on people's faces. Oh my God! Now, there's no law written down that says thou shalt not decant wine with a blender. But my God, implicitly, the idea, the reverence that people have for wine, the mystique, the hushed tones, you pour wine in a blender, you hit frappe, and it freaks people out. Even though it has a better, I've done it, I did it once for one of the best winemakers in Spain, with his Pride and Joy Rioja. And I thought he was going to kill me on the spot. Then we did a blind taste test, and he preferred the blended wine. Whereupon he instantly believed I had tricked him. He says, "We do another bottle. This time I watch." So it's a great example of modernist cuisine in action. You break a rule. It actually has some real benefit to breaking the rule. But you also reinforce for the person, guess what? You didn't think you were an anti-blender for wine bigot, did you? You were. Invention is really important. No steakhouse tells you that they invented steak or baked potatoes. You go to modernist restaurants, and they have enormous pride in having invented the things that they did. In fact, when the book first came out, a bunch of chefs called me up, and they said, "Hey, is it okay if I use that thing on page 350 in the restaurant?" I said, "I published it in a book, dude. I mean, yeah, that's why we publish it in a book." But there's a strong ethic that they wouldn't want to copy somebody else if it looked like they were being either uninventive or if it wasn't welcome. Science and technology are sources of inspiration. Now, cooking is still an art. And I get asked by lots of people to say, well, isn't it an art? You bet it's an art. But you do a lot better art if you know how your damn canvas works. Ask Leonardo da Vinci. He experimented with the techniques of painting and actually lost some of his best work because he didn't have that figured out. And this is more important stuff. Of course, you want great ingredients. A lot of people will say, God, isn't this different than farm-to-table cooking? I say, no, actually it isn't. All chefs love great ingredients. We just think that you can do stuff with great ingredients. And technique often, I'll show a couple examples, technique is often about isolating and improving and celebrating tastes and aspects that are in an ingredient, not the opposite. So this is one of our menus. Besides doing an overly large book, we do overly large dinners sometimes, where we've had chefs and food writers from around the world come and have dinner. We typically cook 30 or 35 courses. So there's no choices on this menu. That's survival, that's the choice. So here's the dish we usually start with. Watermelon chips. We were writing the there's a big section on food science of plants. We were writing about potato chips and how a potato chip forms. A potato chip is a version of something called a starch glass. Matter can arrange itself as a crystal. We're all familiar with crystals, but if it cools in just the right way, you can create something called a glass. The material we all know as glass is the most common example of a glass, but in fact, potato chips are a starch glass. So I decided that I would set a goal of making watermelon chips. Because if you make watermelon chips, you can kind of do anything. But how? So we figured it out, and it turns out it's really simple. Watermelon doesn't have any starch in it, so you can't make a starch glass. So you add starch. We take watermelon, slice it paper thin, put it in a sous vide bag with a little bit of starch and water, a little slurry, suck the bag down. It would also work without the suction, but the suction actually takes residual air out of the watermelon. And what you get is something that you slip into a deep fryer, and the starch in it forms the glass, but the taste is all from the watermelon. So this works with watermelons, it works with jalapenos, dill pickles, apples, just about anything. So back to the menu. Whoops. Oh, let me go back. There we go. So another thing, this is at the other end of the meal, we often serve a pistachio gelato or a hazelnut gelato. And I love gelato. And I love pistachios. But the problem with pistachio is it's a fairly mild flavor. And by the time you add milk or cream and you add eggs to it, it dilutes that flavor. So most pistachio gelato is actually green flavored gelato. It doesn't really taste like gelato anymore. It's kind of greenish. Often that's from food coloring, just to pump it up a little bit. A common trick in Italy actually is to add almond extract, because almond extract gives you some nuttiness without, and in a green context, you kind of think it's pistachio. So we decided we could do better than that. And this is during a period when we were working on emulsions. Now, I believe that you've had a class on emulsions. And of course, emulsions are where you try to mix the unmixable. You take two things, liquids, a polar and a nonpolar liquid, and you try to mix them, so it's oil and water. Cream, dairy cream, is simply milk fat that is emulsified with water and stabilized with a little bit of protein, the proteins that are naturally in milk. So after a while, we said, you know, we could actually do that. So this is our pistachio gelato, and it has no milk, no cream, no eggs. It's made out of pistachios and sugar and a little bit of stabilizer. So what we do is we grind our pistachios and separate out the oil. You get this wonderful green, deep green oil. Then we emulsify it in water. We add the pistachio solids back in. We add some sugar, and you have pistachio ice cream. So it is cream that never went through an udder. And it tastes intensely of pistachios. It's just, if you love pistachios, it's fantastic. And it's a great example of doing something that involves lots of technique. It involves some fancy equipment I'll show you in a moment. But it also is about celebrating pistachios. It's about making pistachio ice cream that's more pistachio-y, has more pistachio-ness. You'll see why I say that later. Than it would otherwise. So here's one of the machines we use to do this, although you can use a blender or a hand blender. This is a rotor-stator homogenizer. It spins insanely fast. You can see it's sucking in little droplets of oil and pushing them back out through some little slots. Whereas a conventional blender will generally make about 10 micron droplets if you do a really good job with it. You can get down to 1 micron with this. So it's really great. Now, besides that, we do lots of other things with constructed creams. In fact, we have the world's only kosher veal in cream sauce. Now, veal is actually the same kind of thing as pistachio. It's a mild flavor. And because it's mild, by the time you take veal stock, you add lots of cream to it, you get cream sauce that's not so veal-y. So we take veal fat and render it so we get the pure fat. Then we take a veal stock, then we homogenize the two. Again, we have a cream of veal, but it was never its mother's milk. So now we're going to talk about another dish. This is our ricotta gnocchi pea juice and pea butter toast. And the cool thing about this is centrifuging. So cooking items have different densities. This is actually a Hungarian goulash we made. And then we spun it up in the centrifuge. It separates out into actually 8 layers by density. The boring one, milky sort of one, is water. But then you've got tomato paste. You have oil, of course, goes on top because it's lighter. And all the way down at the very bottom are the cracked peppercorns that went in to make it spicy. And then each of the other spices has put itself in its own little layer. Now, centrifugation is fantastic for clarification, concentration, or creating new ingredients. Because what it does is by spinning bottles in this machine, you get a pseudo-gravitational effect, which in the case of our centrifuge is about 40,000 times that of normal gravity. So if you have any density difference, it very quickly settles out. In some cases, you could get it to settle out if you're just really patient, you put it in the fridge, but in most cases, it would actually go bad before it ever would, just because it has a time constant of weeks and weeks. Here, you can make it happen much more quickly. So we start with fresh garden peas, although most of the time, we actually start with Jolly Green Giant. There's an interesting thing that it's almost impossible to get peas that are as good as fresh peas unless you literally have the pea vine in your backyard and you clip them right into the pot. Peas tend to convert their sugars into starches after being picked very quickly. And when they have peas, commercial peas, they actually have trucks freezing them in the field. So amazingly enough, frozen peas are a great thing to do. So we take this and we puree it. And it's raw peas, we defrost them and grind them up, and we put them in the centrifuge. And here it is coming out. Here is what we have. Now, if you look at these closely, you can see that there are now 3 layers after spinning. I've got a top layer that is a pea broth. I have a bottom layer that's sort of light-colored. That's pea sawdust. It's a bunch of starches and other parts of the pea. It doesn't have a lot of flavor. We actually make gnocchi out of it, or we make pasta out of it. We add just a little bit of flour because it's a very floury, not very tasty. And you see that little dark stripe in the middle? We call that pea butter. It's not fat. It's not butter. It'd be in the wrong place to be fat. It would have to be floating on top as the top layer if it was a fat. Instead, it's particles of pectin and a variety of other flavor compounds in the pea. And oh my God, is it good. Here's a little video that will show how we do it again. Here we have, we've pureed it. It's going into the centrifuge. Very important to balance your centrifuge. If you've ever had a Sneakers in here it is coming out. Sneakers in a dryer will go ka-whumpa, whumpa, whumpa. Well, the ka-whumpa with one of these will just shatter things. Here's the pea butter being put out onto toast, and you can see it's got this wonderful shiny texture. There is the pea broth that's being poured. Here's a sort of a close-up of the pea butter. It's on a walnut toast with coarse salt on top. Here is the pea broth put on some garden vegetables. So I was explaining this in a talk in New York, and I was saying about describing a different recipe, how it was really beefy, and so it improved the beefiness. And I was then enthused, so I got out of this, and I said, so this really improves the pea-ness. So at least I didn't say it accidentally this time. I was completely accidental when I said it before. Okay, next recipe, caramelized carrot soup. Now, when you see caramelized, in almost all cases, they're wrong. There is a wonderful thing called caramel, but whenever you're talking about a caramelized food, it's almost always some version of the Maillard reaction. But Maillardized doesn't sound good on a menu, whereas caramelized does, so cooks tend to call it caramelized. Now, the great thing about caramelizing stuff is that you get this wonderful brown colors, you get a bunch of interesting flavors. It's a fantastic way to cook any vegetable that has some sweetness to it. Normally, you have to get the temperature pretty high. In particular, the temperature has to be higher than the boiling point of water. So it only browns once it dries first, and that gives you a bunch of problems. But that's not true if you do two things. If you increase the pressure, you can make the temperature quite hot and not have water boil. And if you increase the pH, you make it more alkaline, you can actually make the chemical reactions responsible for the browning occur at a lower temperature. So here is a pressure cooker. Here is a pressure cooker cut in half. This happens to have stock in it. We love making stock in a pressure cooker. And of course, as you know, if you increase the pressure, you can boil at higher and higher temperatures. What we call the boiling point of water is really the boiling point of water at normal atmospheric pressure. Lower pressures, you can boil water even at freezing, actually, even below freezing. That's how freeze drying works. And you can boil it, obviously, at higher pressures. So if you typically use about 15 pounds overpressure, that means you've about doubled the atmospheric pressure. You can cook up to about 250 degrees, 121 centigrade. It's great for two reasons. One is it naturally stays exactly at that temperature. So it's the spring-loaded valve is effectively a pressure gauge, but it's also a thermostat. So that's great. But the other thing that's great is by raising this up, you can get the high temperature without boiling the water away and drying the food out. Oh, here's our stock tables. We've got tons of tables in the book. Here is the soup. This is what it looks like afterwards. And now we'll show a video. So to make this, we start off with carrots. We cut them in quarters lengthwise, and we cut the core out. And the reason for this is the core actually is substantially more bitter than the rest. If you make carrot juice, try cutting the core out. You'll be amazed. So now we're putting a lot of butter in. We put butter directly in the pot. Then we add the carrots. Stir well. Here's the magic part comes next. We're going to add some salt, but we're going to add some baking soda. And the baking soda is the key thing here. That's the soda going in. About 0.5% by weight. Typically, salt is 1% by weight, just by the by. So stir this up. Now, the interesting thing is we're not putting any water in because we don't need any extra water. We seal this up. We bring it up to pressure. Little red line tells us we're bringing it up to pressure. Cooks for about 20 minutes. It comes out, and it's now browned. And not only is it brown on the outside, it's actually browned all the way through. So we've caramelized carrots. Now, what we do next to make the soup is we simply put it in a blender and grind it up. So I'm often asked by people about how complicated are the recipes. Well, here's a recipe where the ingredients are carrots, water, salt, baking soda. It's pretty simple, but it's also fantastic. And we've had the pleasure of cooking this for some of the best chefs in the world, and they're amazed. Not only amazed at that you can, by the flavor and so forth, but amazed that you can do it in 20 minutes without drying it out, without doing the other steps. It also works for onions, for beets, tons of different vegetables. Here's another cutaway photo. This is our hamburger cutaway. Well, people often ask how we do this, and of course we cut stuff. We have a machine shop. That's really how we do it. But then they say, well, how do you keep stuff like, how do you keep those coals from falling off? I say, oh, we didn't. They fell off. There's a guy beneath there with a pair of tongs, and every time that they come off, you put it back up. And our motto was very simple. It only had to look good for 1,000th of a second. You know, if it all went to hell afterwards, so what? So, you know, cooking with pots cut in half is terribly messy, often dangerous, but if you do it right, you get some cool shots. The point of that was really to explain that grilling and actually the properties of a hamburger come from a bunch of scientific principles. One is the flavor of grilling is largely from those fat flare-ups. When fat drips down and it has those flare-ups, the incomplete combustion and pyrolysis from that creates grilled flavors. People who grill vegetables often wonder why they don't have all those great grilled flavors. The reason is they don't have any fat dripping down. So if next summer when you're grilling corn or you're grilling zucchini or something like that, slather it with oil or butter, or what I do is I have a squirt bottle full of it. You squirt it in the fire, and boy, you get the grilled flavor. So we did this hamburger because we wanted to illustrate a bunch of different techniques. We discuss how to grind the meat. It turns out there's a specific way to grind the meat that makes a difference. We make the bun. Every single part of that hamburger we have gone and optimized because we have a philosophy that it's important to consider any food as valid. And it's just as valid to make the ideal hamburger as it is to make a coq au vin or bouillabaisse or some other dish that's far more celebrated. It doesn't mean you always eat the ultimate burger, but it means that you do at least, intellectually, it's worth at least exploring what it would do. Now, one of the things we came after having the ultimate all this is how are we going to cook the burger? What's the ultimate way to actually cook the burger? We came up with a technique called cryo-frying. We cook things sous vide, we freeze it in liquid nitrogen, then we deep fry it in oil. Now, the sous vide step is you cook stuff typically in a water bath. Here we're cooking some small fish. With the hamburger, it's actually important not to seal the sous vide bag. The pressure of sealing the sous vide bag makes the patty too dense, at least by our taste. You cook it at very low temperature. We cook it typically at about 125 degrees to 130 degrees Fahrenheit. That makes it cooked. But then liquid nitrogen comes in, and now we're going to deviate from the demo. Now, it's very important to have safety gear. This is liquid nitrogen. So we're going to pour some in here. Now, do you notice I'm pouring awfully fast and the level's not coming up? That's because I'm boiling a lot of it as it comes in because the dewar is warm. Okay. Now, this is vigorously boiling because, of course, the boiling point is at minus 196 centigrade, about 321 Fahrenheit. Now, one thing you should never, ever do with liquid nitrogen is that, or do this. The reason I'm able to do that is because the liquid nitrogen has got two properties that make that a possible thing. The first is that it doesn't have that much, the latent heat of fusion, the amount of energy it takes to boil liquid. Now, watch how it's cooled down, how it's calmed down. I'll tell you why in a second. Boiling liquid nitrogen doesn't release as much heat as require as much heat, as boiling water. So although as it boils, a lot of heat is coming out, it's not coming out as fast as you might think. But the other reason you can do that is that as I dip my finger in there, it boils around me in something called the Leidenfrost effect. And so you get a thin layer of nitrogen gas around the outside. And nitrogen gas doesn't conduct heat very well. We will return to the liquid nitrogen in a moment. Somebody earlier asked if chefs actually have groupies. The answer is no, the flour is part of the demo. So if you do freeze things in liquid nitrogen, however, they can become very brittle. Here's a piece of corn that we hit in our lab. So the hamburger comes out of the sous vide, it goes into liquid nitrogen, and then we need to cook it. Now, why liquid nitrogen? Because we want to get the outside of the hamburger and maybe the first millimeter of the hamburger to be intensely cold or frozen. Because then when we put it into the deep fryer, we can heat the outside, but there's a cold barrier. And that barrier prevents the inside from overheating. So it's about 30 seconds in the liquid nitrogen, then it goes right into the hot oil. Here it's going into the hot oil. Here it comes out. The reason that it's great to cook this in hot oil, by the way, is that you've got lots of these cylinders of meat in a hamburger, and there's little crenulations and crevices in between them. Well, if you put it on a grill, it only gets the surface, but the oil penetrates so it gets crispier. Now, here it's calmed down. The reason it's calmed down is there's super cold nitrogen now in this layer up here, so now it's insulating the nitrogen from the whole rest of the room. So that's why I didn't leave my fingers in there for very long. Once it gets cold enough that liquid nitrogen starts closing in, it gets cold in a hurry. So you can easily do that, but you don't want to leave it in there for long. Okay. This is the result. So the hamburger is medium rare, except at the very edge where it's cooked. And it's very hard to achieve that if you don't use liquid nitrogen. Of course, at the actual surface, the meat's browned. It's the Maillard reaction again. This is a photo that I took of meat browning. It's about 2 millimeters across the whole frame. The part that's actually brown is extremely small. And the reason is, it's got a huge heat sink behind it, but that heat sink is full of water. And when you put a steak in a pan, all that bubbling, that comes from little steam volcanoes underneath the surface. You can see we've got some arrows drawn about here. That's the boiling zone. That's where the steam is being generated. And it's only the extreme edge, a fraction of a millimeter, that actually is raised enough above the boiling point that it can brown. And when you look at it, it's actually a gel. It's a clear gel. The optical properties, when you look far enough away, make it look different. Also, you see the layer of white? That's not fat. That's cooked beef. When you look under a microscope and you put enough light on it, beef's white. When you zoom back out, there's enough vesicles around it. There's some other things. It gets this kind of a grayish thing, and you get a little bit of brown from the edge. But it's actually quite white. Here's another piece of cooking physics. Broiling is about cooking with light. And there's an interesting thing that happens here. This happens to be a technique for cooking fish, but the rate at which the food absorbs depends on the color of the food. If it's white like a fish belly, or actually a lot of food, white sort of things, it's actually going to reflect most of the light. The darker it gets, the faster it absorbs heat. So here's a piece of toast at 1 minute. Here's 1 minute later. Here's another minute later. It's getting substantially darker. But as it gets darker, the rate at which it continues to pick up heat gets higher, because now it's darker and it's absorbing more. So now in only half a minute, look how dark it got. And in another quarter of a minute, it goes fully, it becomes burned. That's because when you start, the piece of bread to begin with is actually reflecting about 90% of the light. It's only absorbing about 10% of the infrared light that hits it. At the black end, it's the other way around. So the absorption, the rate of cooking, increases by a factor of 10 just as you cook, which is why it's incredibly hard to judge the doneness properly. You have to watch very closely because it goes super fast. We did a bunch of stuff, although we don't really do baking, pastry or dessert. We did soufflés because we wanted to cut one in half. We thought that would be fun. Very interesting things that go on here with how the bubbles are formed. And fundamentally, the bubbles in a soufflé, the soufflé is formed differently than bread. In bread, the bubbles are formed by chemical reactions. The yeast actually exhale the carbon dioxide that makes the bubbles. In the case of a soufflé, you put the bubbles there yourself. You beat the eggs. So why does it puff? It puffs because you make the bubbles bigger. And it makes the bubbles bigger because two things happen. You get them hot, and hot gas expands, number one. Number two, you start evaporating water because you get close to the boiling point. As you evaporate water, you're puffing it up with water vapor. That's also why soufflés collapse. When you cool the soufflé, when you're taking it out, that water vapor condenses and actually creates a vacuum, and it can suck the thing down. So here's some of the different stages. Here's another explanation of water going. Watch this closely. This is popcorn. When water boils to steam, it expands in volume by a factor of 1,600. And that's what's happening here. When it starts out, it is, let me just go back one and do it again, because that one's kind of fun. Whoops. So what happens is a tiny fissure opens up and it becomes a steam rocket, and steam is shooting out, causing it to lift up. But watch it expand. It's trying to relieve pressure more than that, and this fissure is going in, and finally it gets an abrupt failure of the outside. I should say that while we made the book, we had a high-speed video camera, and they are just enormous amounts of fun. I've got some gratuitous high-speed videos at the end. Here's a different way to make foams. This is using a whipping siphon. This works because nitrous oxide, the gas that you put in there, is highly soluble. So you dissolve it, and at pressure you can dissolve a lot of it. You release the pressure, it comes out, it bubbles up. That allowed us to make an instant souffle. This is one of the most difficult recipes we did in the book. It took us 150 attempts to make this. I was discussing this at a talk I gave in New York last week, and some guy in the back says, "I made it last night, it still works." And now I have some gratuitous videos. This is a water balloon. And the part I love about this is that no one's told the water it's time to fall yet. Okay, this is like the, you're probably all too young, but the Roadrunner and Coyote cartoons. You know, you only fall if you look down after going over the cliff. Yeah, a more physics way of saying it is that the outside of the balloon is under considerable tension and has very low mass. So when you prick it, it opens up, it catastrophically fails, and it's got lots of force that's whipping it out, and it doesn't have much inertia. There's a lot of inertia in the water, and so it takes a while for it to get going. Here's a cool thing. This is zesting an orange. Now, when you zest an orange, what you're trying to do is get the oil out. Okay, it's not the oil zest that you put in your food. The zest isn't important. It's the oil that's in it and the oil that comes out when you do it. So we want to have a way of demonstrating the oil in it. So try that with a zester next to a candle. It's awesome. So we have a chapter on gels. And I decided that no chapter on gels would be complete without a recipe for ballistics gelatin. Because everybody sees it on CSI and Mythbusters. Well, you have a high-speed camera, you have a block of ballistics gelatin. Pretty soon somebody says, you know, we could get a gun. Turns out ballistics gelatin is the same gelatin you eat for the same dessert gelatin. But if you want to make an omelet, you got to break a few eggs. So once you're set up with a ballistics gelatin, someone says, hey, what else can we shoot? So. And with that, I'm done. I'll take questions.
So we have people walking around with microphones, so hold your hands up. Is somebody there? Max? Max?
Thanks. Hello?
Yep.
Is this on? Can
Yeah.
you hear me down there? Great. Thanks. Lovely presentation. Amazing work. And I just want to thank you so much for sharing it all. And so I'm wondering if you'd talk a little bit more about how sharing is important for the creative process in cooking and how that relates to your patent processes with your company, Intellectual Ventures.
So, well, you know, one of the things that's very interesting to us is that within the community of modernist chefs, there is a tremendous amount of sharing. Sharing and building on other people's work is central to science. It's also central to a lot of innovation-oriented disciplines. The way it works in cooking is that people will invent a dish, they'll publicize it, they'll go out there, and at that stage they kind of have bragging rights on that dish. We have in the history chapter, we have a whole list of some of the key dishes or technique innovations and who came up with them first. And we sent it around to a bunch of people. Of course, everyone thought theirs was first, and not everyone really was. Now, science works exactly the same way. Science works on the basis that if you publish first in a peer-reviewed journal, then it's yours. And it's yours in a credit sense, but that's how you get paid and how you get further grants. Most cooking things aren't actually relevant for patenting because they're neither the type of thing that is covered by patents, nor are they the type of thing that you could actually make any money on with patents. So people in food typically don't file patents unless they're things you can make by the ton. So the place where you find patents in food tends to be in commercial processed foods. And so in the process of the book, we actually invented one technique, one or two that we did file a patent on. One of them is for a better way of making French fries, believe it or not. Because that's the type of thing that potentially you could license to a food company that would then make tons of French fries. The patent system is actually very parallel to these systems of credit and ownership that exist in science or in cooking. In the patent system, instead of publishing in a peer-reviewed journal, you publish in the patent office. You get a period of time for which it is uniquely yours, at least from a commercial standpoint, it's uniquely yours, and then it passes into the public domain. And the idea behind it is to try to reward people for their invention so they would have a financial interest in doing it. As I say, it doesn't come up very much in cooking. A couple years ago, though, there was a modernist chef, a guy in Australia, who went around the world being a stagiaire at famous modernist restaurants, including Alinea in Chicago, WD-50 in New York, and some others. Then he came back to Australia and opened a restaurant featuring exact replicas of each dish without crediting the original chef. And 20 years ago, he probably could have done that forever and no one would have known, or it would have taken a long time, but with the age of the internet, like the next week, it was all over the place. And a lot of chefs got upset, and they said, well, gee, can't we have some legal protection? The answer is there isn't any legal protection for that kind of thing, for the presentation of the dish and so forth. You could, in principle, get a trademark or a copyright on it, in principle, but in practice not. So intellectual property for chefs is I was then interviewed endlessly because I'm a guy in intellectual property and in cooking. Mostly, though, patents and that kind of invention is not something that's relevant to science in the kitchen. And frankly, most chefs aren't that into it. There are, however, amateur chefs. One of the phenomena we cover in the book is something we call cult foods. So there are various parts of the world where there's a food that people invest lots of regional identity in. In Texas, chili is a good example. In Marseille, bouillabaisse is a good example. In Toulouse or Carcassonne, it's cassoulet. And whenever you have one of these cult foods, you always have secret recipes. And so the people in Texas have their secret recipe. They won't tell anyone. They won't tell their own kids. It's this whole thing. It's very funny to me that there you find it. And every chef that we talked to about putting a recipe in the book was thrilled to do it. It was sort of the opposite of what people expect. It actually tends to be these cult foods that are done on an amateur basis where you have fierce secret recipes. Some restaurants probably, but the very best chefs, Ferran Adria, for example, is ridiculously open about things. I mean, when I've eaten there at the restaurant, if I have even the slightest question or look quizzical, he or his chef de cuisine will come over and they'll start showing me how the dish was made on the spot. Okay, next question.
How long have you been working on the book, and what's the most difficult recipe?
The most difficult recipe was the instant souffle. The goal of that, I should explain more. The goal of that instant souffle was to make a souffle base you could put in a whipping siphon. Then, if you wanted it to, and you could keep it warm or refrigerate it, then if you wanted to bake the souffle, you just squirt it into the ramekin and put it in the oven and bake it off immediately. It turns out that's hard. And it's hard because you have to stabilize the bubbles in the souffle one way while it's cold, and a different way while it's hot. And so coming up with the right mixture of stuff took us 150 trials, but we eventually got something to work. In terms of how long it took me, I made the first outline for the book in the fall of 2005. We sent it to the printer in fall of 2010, so 5 years. 2 of those years I was alone. I'd still be working on it if I was alone. That's why we hired up a whole team of people, because this kind of work is something that you just couldn't tackle by myself.
Hi. So chefs are usually distinguished by their ability to employ many great techniques and cook food in what would be the most proper way. And with the advancement of modernist cuisine, surely that's developed. But they're also distinguished, I think, by their ability to create innovative flavor combinations. And I was curious if your scientific, excuse me, if your scientific research has done anything to help us understand why certain things taste good together, like peanut butter and jelly, French fries and ketchup.
No. Next question. No, no. So there's a popular theory of taste that suggests that there's, depending on who you talk to, 6 or 7 key tastes: sour, bitter, salty, sweet, umami. And people argue about umami. The interesting thing is, it's not true. Now, our vision does work that way. We have receptors in our vision that can really see 3 different colors. That's why RGB monitors work. You can get any possible color by mixing those 3. For many birds and insects, there are 4 such things. They have a receptor in the ultraviolet. It's almost impossible for us to understand what they see. Just like it's hard for us, if you walked around wearing a red filter, a green filter, so you were filtering out some of those other components, you'd see a very strange-looking world. Their world is stranger yet again. So people thought maybe all taste is a combination of those 5 components. It isn't. People mapping the tongue have discovered that, in fact, there's at least 40 different receptors. Some people argue there may be hundreds of receptors. So it's not a component. The great thing about color is it's a short vector. It's a 3-component vector. It's great. Any color is 3 things. Any taste is not 3. And so for that reason, it's hard to have a comprehensive notion of flavor. So then people have tried to do a bunch of things where they say, well, let's try to empirically or semi-empirically come up with some theory as to what flavors match with what other flavors. There's a website called foodpairings.com or flavorpairings.com. I think it's foodpairings.com, where it's a sort of an empirical database of things that look good. And most of those things are intriguing, but there really isn't very much scientific proof behind it. So the predictive value of these sort of semi-empirical things just isn't very high. Now, there's an evolutionary way that you can understand what things taste good. That's quite different. We like fats because they're nutritious. We like sugars pretty much for the same reason. So a lot of the things, human beings like the smell of a fire. Weird thing, most animals run from fires. There's an anthropologist named Richard Wrangham, who's here at Harvard, who's written this amazing book called Catching Fire. And he posits that, in fact, a fundamental part of the evolution of humans is that we learned how to cook. And as part of that, we are attracted to wood smoke and those kinds of flavors. We're attracted to the kinds of flavors that food acquires when it gets heated. And that allows us to eat with the pathetic little mouths that we have. I've got a picture in the book of a gorilla that I took in Rwanda. And he's yawning. And you can see the kind of dentition you need to have if you want to subsist on raw vegetables. Okay? This is why vegans have blenders. Okay? You literally can't get enough nutrition from raw vegetables with the pathetic teeth we have. You need to have a blender. And with a blender, it works fine. So that's the evolutionary reason that some things taste good. But then there's lots of other mysteries. Why do truffles taste good? Truffles could not possibly have an evolutionary advantage from our perspective in tasting good because they're not big enough, they're not common enough that they could ever have been an important food for us. The answer there is evolution on the truffles part. The truffle wants a pig or some other animal to eat it and crap its spores out all over the place. So it figured a way, it evolved a way to fool mammalian taste buds into loving it, even though you can't describe what the hell it tastes like. You know, you say it's like the earth. Yeah, but I don't see eating a lot of dirt that way. Okay, next question.
My question's about the future, I guess, because you've done so much work to, like Escoffier, he categorized traditional French food. You've essentially categorized modern food in general. David Chang was discussing microbiology last week as a possible future of food. I know Noma is, at this point, the future, but he's also doing microbiology. So I'm just curious what your thoughts are about...
a chapter in Volume 1 called Microbiology for that very reason.
As far as what you think as being, like, I mean, now that, you know, LBE, the most creative restaurant, is now a think tank, what is next, in your opinion?
Well, part of it being a think tank is so that there's, Ferran can create more without the hassle of having to feed everybody every night and whine about not getting a reservation and so forth. So here, I'll give you two perspectives. The big picture view is this. You have never had a broader diversity of food choices today than at any other point in human history. There's more foods available in Boston or New York or any place, more now than ever before. And a huge amount of that came by importing new foods. You know, 20 or 30 years ago, it was hard to find sushi in the United States. Now you find it literally everywhere. Lots of other cuisines have been imported. And so we've had this monotonic rise in the diversity of foods. But we can't keep importing it because we're done. Okay, there's not like 10 more wonderful cuisines like sushi out there waiting to be discovered. We've been everywhere on Earth. We know what they eat. And yeah, there's a few things that may not, you might say, oh, well, there isn't a really great X restaurant in Cambridge. Although Cambridge probably has a better shot at it than most places in the United States. But fine, there will be. If it's worth eating, you'll have a choice to eat it, and pretty much that's been the history of cuisine. But because we've run out of the importation, there's only one thing we can do to keep up the diversity. We either settle for less diversity, but there's no evidence we want to do that because people love the idea of, hey, let's go out and have Thai food. And let's have, Chinese food used to be one thing. Now it's Hunan or it's Szechuan or it's Western Frontier and it's all other types. So we have to invent it, plain and simple. And of course, we also have invented food continuously over a long period of time. One of the things that is a real myth is the notion that there's such a thing as traditional cuisine. Cuisine is always changing. It's not like there's this big tradition, and then all of a sudden there's new stuff. Tradition is a bunch of old innovations. Michael Pollan has this great guy, fantastic writer. He's been out to our food lab. I love what he does. He loves what we do. But he has one of his precepts is slightly too simple, and it says, you shouldn't eat anything your great-grandmother wouldn't eat. Well, great-grandma didn't have sushi, but damn it, I'm going to have it. And besides sushi, there's all kinds of things that were invented. Widespread use of ice cream. And then if you go around the world and you say, how many great-grandmothers ago various foods happened? 2 great-grandmothers ago, there were no tomatoes in Tuscany. It sounds crazy, but it's really true. In fact, oddly enough, Tuscany was about the last place in Europe that tomatoes were accepted. And the reason why is the same reason that Michael says you should question what grandma didn't eat. Everyone was afraid it was poisonous. It was bad for you. It was a perceived health risk. And it wasn't crazy either. Tomatoes are part of a nightshade family. and the leaves and everything are very similar to the nightshades, which are poisonous plants. So everyone's like, I don't know about that tomato thing. So anyway, I think looking forward, we're going to see lots of new innovation. Microbiology has got lots of possibilities for that. The extreme versions are people are talking about growing meat in a vat. Right? Why grow the whole cow if you really want or the whole pig if all you want is the bacon? People are already growing truffles that way in Oregon. There's a company that grows truffles in liquid tissue culture and filters it out. Unfortunately, they grow Oregon truffles, which kind of aren't worth eating to begin with. So it's not clear how successful it is. But at some point, we're going to have the ability to radically change the way we eat if we really want. And by the way, we'll have a lot of motive in doing so because the whole world is going to want to eat that way. It used to be that the ways the United States eats was unique in the world because we were a rich country and most of the world was poor, but the rest of the world's getting rich quickly. And one of the first priorities they put is on eating better. And eating better to most people means eating more meat. Yeah.
Could you comment briefly on your photographic techniques? These don't look like 35 millimeter slides. 35 millimeter digital.
They are.
Done.
All the photos in the book were taken with Canon digital cameras, full frame, 5D Mark II, 1DS Mark III. So. The thing about the photos is we wanted to show the world a vision of food they hadn't seen before, which is non-trivial because the world's seen food photos for a long time. But it turns out let me start over. The reason we were able to do it is that people focused an incredible amount on simply making food look appetizing in a conventional way. And as a result, they didn't try to cut pots in half. They didn't try to show what was going on. They weren't trying to do a scientific look at it. And because they didn't have that motive, they left all those techniques for us to discover and invent. And it was a lot of work, but ultimately I think it's been pretty successful in communicating the message of the book.
Hi. I guess I was wondering...
I took a lot of the photos myself. My assistant took 90% of them, though, because I got busy.
I guess I was wondering if you were a basic home chef, like what tools would you prioritize getting? Because you clearly had access to things that I don't think I'm ever going to have in my home kitchen, like a centrifuge.
So what I usually say is that about half the recipes in the book anybody can do. And you might have to buy a few little pieces of equipment. Probably another 25% you can do if you're willing to buy a little bit of equipment or some unusual ingredients. And the last 25%, good luck. and there's a few things that even a kitchen like El Bulli, good luck, because we have some pretty exotic stuff. I thought it was okay to not dumb the book down and do that, because hey, half the recipes is still 750 some. In terms of prioritized lists, we have several prioritized lists in the book. The simplest thing is you should all have a digital thermometer and a digital scale, and they're like less than $50 each, so like there's no excuse if you're serious about cooking about having those two things. When it gets to more expensive, now this stuff, by the way, this costs less than Fiji water. So people, liquid nitrogen is really exotic. It's not exotic at all. It's 78% of the air around. The other people say, well, is it dangerous to have in the room? Well, good luck. There's 78% of the air around you is nitrogen. So to manufacture this, they just have big refrigerators that cool air down, and this drips on out. So we have a whole prioritized list. Sous vide equipment is probably the first major purchase I would recommend doing. And that used to be hideously expensive because it was only laboratory equipment makers that did it. Now it's coming down in price. You can get them for $300 to $500 for the simple ones, maybe $800 for the fancier sous vide setups. But over time, there's no reason that shouldn't be the price of a slow cooker. It's just there's a transitional period as the volume grows and people try to re-engineer them for cost. Pressure cookers are fantastic. We love pressure cookers, though, and those are cheap. Yep.
So, like anyone raised in a strict kosher kitchen, I'm a really big fan of veal cooked in cream sauce.
Yes, there's a friend of mine who says if this really, really works out, I will be buried in the cemetery for righteous persons. I'm not sure that's true, but...
So, can you explain, is it really kosher? I mean,
well, okay, see, I'm not...
concerned.
Look, I got a PhD in quantum physics, and I wrote this book, but I don't claim to understand everything. No, I am told it ought to be possible to make that in a completely kosher way because, in fact, it's only faux cream. It's not actually cream. And the specific restriction is about cooking an animal in its mother's milk. So because there's no... because the fat itself isn't non-kosher, nor is the meat, and whipping it up with water probably wasn't covered. A little bit like decanting wine into a blender. There probably isn't a rabbinical order against, emulsifying fat. But I'm not a rabbinical scholar, so don't take my word for it.
How would you cook a Thanksgiving turkey?
I'd change the topic and cook something else. So the problem with turkey is that turkey is just intrinsically a difficult thing to cook. It doesn't have a lot of flavor, particularly in the breast. But the breast has very different cooking properties than the rest of the bird. So roasting a whole bird is not a good way to cook it, unfortunately. So for cooking the breast, my favorite way to cook the breast is to steam it, but I would low temperature steam it or cook it sous vide. And then it can be as moist and flavorful as is possible for it to get, which isn't infinite. Or you could low temperature smoke it to add some flavor so it would have some. And if you wanted it if you wanted to overcook it, you could brine it first so that you could overcook it and it wouldn't be so bad. Turkey wings and turkey thighs I have some enthusiasm for, particularly the thighs, but the wings are actually amazingly good. But there what we do is we cut them off the bird because in the context of everything else, by the time they're cooked, the white meat is gone. If you cooked it to only cook the white meat, it would would not be done. So there we cook it sous vide at low temperature in a bag for 12 hours, something like that, at maybe 150 degrees Fahrenheit. And then it becomes wonderful and unctuous. With the wings, you can poke the bones out and then throw them in the liquid nitrogen for a minute, then in a deep fryer. That's great. But the simplest way to cook it at home is to say cook thighs separately. The drumsticks are nice too, but the drumsticks have lots of big, thick tendons in them, so they're a little bit harder to cook. So my favorite way of cooking turkey would be thighs and perhaps and breast, but cooked very separately. And once you cook it separately, lots of techniques work. The trouble is getting a compromise between the two in a single bird, which tradition dictates, but is suboptimal cooking-wise. Yeah.
It strikes me that science and cooking can still be very empiric. Can you give us a sense of how many things you try before hitting a home run? I mean, what's your ratio of sort of failure to success?
Well, there's some things we're still trying. We're stubborn that way. It depends. In the case of the recipe that had the most trials before it went in the book was that instant souffle. And in that case, it kept sort of working. Otherwise, we would have stopped at some point. There were other things where we had a theory, and our theory was wrong, and one experiment convinced us we were wrong. It's like, okay, move on. And then, of course, there's lots of happy accidents that occur. And you say, wow, that's pretty cool. That liquid center chocolate cake that they showed a picture of earlier that the class did a test on, the most popular recipe for that came by a complete accident. Chef named Jean-Georges von Grichten was cooking for a large party. They made the cakes bigger than they normally did. They cranked the oven up to try to compensate. They rushed the cakes up because everyone was waiting. He tries one. It's liquid in the center. He goes berserk. He screams at the kitchen staff. He says they're all fired because he's going to be fired. It's the worst day in his life. They come and they say they want you in the banquet room. He goes in, they have 300 people for this banquet. He walks in to a standing ovation. Because it turned out the fact it was underdone in the center turned out to be a feature.
One more question.
Good evening, Chef. Unfortunately, it's going to be two. One is related to this book. I mean, it's an incredible project that you've done. And I was wondering about what your plans are related to the future, related to this particular project. Are you planning on starting a think tank similar to Alicia, or a foundation, or putting out future editions or anything like that? Or is this
No. I've had one for 5 years. Certain Johnny-come-latelys are about to get in the business.
So you do plan to continue that as well?
Well, our lab is still functioning, and there's people coming to work every day. We've been very busy since we finished the book almost exactly a year ago, but then we've had lots of other things to do. Corrections to the various new printings of this book. The book comes out next week in French, Spanish, and German. So we had to do a lot of work associated with that. We've cooked a bunch of the special tasting menu dinners for chefs from around the world to show them the food that we have, and that takes a lot of work. And we're thinking about future projects. But we've been so busy this first year with getting this book really launched that we didn't have much time. Starting in January, we'll consider what to do next. There's a bunch of possibilities. We didn't do pastry baking or dessert in this book. And we didn't do that because it's just a world unto itself, and it would have been another 4 or 5 volumes. So in the future, I think it's likely we'll tackle that, but probably not next, because after doing one 5-year slog, you might like to do a smaller project next. And there's lots of smaller projects that we've considered, but we haven't really picked one yet.
Thank you. All right, thank you. And my second question is, this has been, we've seen a lot of these lectures in the past several months, and this one especially is very much related to what comes onto the plate and how it gets there and everything that goes into creating that. But a lot of what I've heard a lot of chefs talk about is that the process of cooking and eating is very much like also two-way. It's the diner as well. And one of the concepts they've talked about a lot is memory and the way that relates to flavor and the way that it affects the diner itself. And I was wondering if you've done any research or have any interest in I guess the psycho-emotional relationship and things that go on related to cooking and eating.
So cooking has very profound psycho-emotional effects, and there's a variety of ways you can study that. You can study it with an fMRI machine, where they strap you in this giant MRI thing, they inject weird shit into your blood, and it tastes awful, by the way. A lot of the contrast agents, here's an amusing fact if you haven't had one of these MRIs, when they put it in your blood, and it takes about a minute to circulate, and when it gets to your tongue, you taste it from the inside. It's got it's the weirdest sensation to be tasting this strange metallic taste, and it's because your taste buds are firing not from stuff on the surface, they're firing from the inside. It's very weird. Anyway, from those things, you can see how various odors and flavors affect people. They affect people very strongly. They light up specific parts of the brain. We absolutely have flavor memory. There are people who have tried to do things like do flashcards with scents effectively, because there's some evidence that if you have a olfactory stimulus at the same time, it helps you recall things. And modern chefs have worked with this. Ferran Adrià has a very challenging set of dishes, very interesting set, where they specifically play upon flavor memory. So what they do is those dishes take a very familiar food and they put it in a very unfamiliar context, different textures, but the same flavors. And the question is then to allow you to confront the dissonance between how it looks and how it tastes. Heston Blumenthal and some other chefs pioneered doing the opposite, where you have something that looks like something but isn't. So that's one where they're both about playing with different aspects of memory and nostalgia. A funny thing about Heston's restaurant is Of course, most of his clients are from the UK. So he has a whole bunch of, he's got this one dessert thing that's a bunch of pedophores that have flavors of the British candies he ate as a kid. I didn't. They really don't mean very much to me. To Brits, they go ooh and ah and get so enthused because it's their version of candies. In the United States, if you had M&Ms or you had Almond Joy or you had a whole variety of specific brands of specific things, there would be a flavor memory that you'd have associated with it, like the flavor of pink bubble gum. I mean, there's lots of those things that are very characteristic. And if you grew up on them, you have them. If you grew up on a different set of brands, so like, what's this dish about?
Okay, so let's thank Nathan one more time.